Hello and welcome to the second lecture of this module, and you know that this module is on probability and statistics, and we in the last class we have started the discussion on this sampling distribution and parameter estimation, and we have seen there are two different methods of this point distribution, and we started that interval estimation, and we completed that interval estimation for the mean with known variance. So basically today's lecture we will continue from the same point, and whatever we have was there for the sampling distribution for the other estimation, that is for the variance and proportion, and those we will see both for their point estimation and for their interval estimation. So our today's lecture outline is that interval estimation of this mean. Basically this we started in the sense that we have used this for the certain when the standard deviation for the population is known. In that case we have just seen, and we have also discussed the theory when the standard deviation is not known, and so we will start from here where in which case that the standard deviation for the population is not known. We will start from that point, and we will start with that example, and after that we will see what is that interval estimation for the variance, and then we will see that both that point estimation as well as for the interval estimation for the proportion. And you know the proportion is generally used for some of these distribution, for example the Bernoulli's distribution that we use there. So we will see those estimates, and if time permits we will also discuss about this test of the hypothesis, what we have mentioned in the last class, that when we are interested about the two different samples and we want to infer something about their respective population, then this test of hypothesis is important. So to start with, we will start with this interval estimation of mean, basically one problem where the standard deviation for the population is not known. So a random sample of 25 concrete cubes were selected from a batch of concrete cubes prepared under a certain process. The sample mean of 25 concrete cubes found to be 24 kilonewton per meter cube, and the sample standard deviation is 4 kilonewton per meter cube. Determine the 99% and 95% confidence interval of the mean strength of this concrete cube. So this is mean density, this is mean density of this concrete cubes. Now if you just compare this problem with the with our last class problem, then we will see that whatever the data is given, that is that whatever the sample mean and the standard deviation, these are numerically same to the whatever the problem that we have taken in the last class. But only thing here is that this is the both this so in the last class also that mean was the sample mean, but the standard deviation was the standard deviation for the population. But here we are using it is with a sample standard deviation, because you can see that this random sample of 25 concrete cubes, earlier it was more than 30, so which can be considered to be the large sample. And you know that we have discussed in the last lecture that when it is more than 30 we can assume it to be the large sample, and for particularly for the estimation of this mean, and when it is less than 30 that is generally a small sample. So we have to estimate the standard deviation from the sample itself, and we have to use that t distribution, standard t distribution with n-1 degrees of freedom to calculate whatever the confidence interval for such cases. So so basically here as you can see that the 24 kilonewton per meter cube and 4 kilonewton per meter cube as this mean and standard deviation is given. What can be happen is that basically that 25 concrete cubes are there, so 25 values are can be obtained from this one, and from there we can calculate what is this mean from the estimator of this mean that we discussed in the last class, that is that x bar is equals to summation of all these values divided by n is here 25. So that we can estimate, and similarly we can use the estimator for the standard deviation to get this one. So here these values are already given just for this, because we are in this problem what we are mainly discussing is that to find out their confidence interval. So, basically the background to this data that is given to us, this 24 as well as this 4, is basically obtained from these 25 different values that is obtained from the experiment. Well, so here the n, that is a sample size, is 25, and we know from our last lecture is that x bar minus this mu divided by s by square root n. Now, this is the s, earlier it was the population. Generally, you know that when we use that English character, English letters, then it is the sample, it is related to the sample, and when we use that the Greek letters, then this is generally to the population. So, this s, when we are using, earlier example we use the sigma, which is from the population, and here the s, it is from the sample, that denotes. So, this x bar minus mu divided by sigma by square root n has a t distribution with degrees of freedom n minus 1, that is n is 25 here. So, n minus 1, 24 degrees of freedom. Now, for the 99% confidence interval, here the alpha by 2 is equals to 0.005. So, this where from we have discussed in this last class that where you are getting this values is that whenever we are talking about this confidence interval. So, if this is the distribution table, then so this area is your that 99%, so 0.99, and so that whatever is remaining here and whatever is remaining here from the symmetry are same. So, this is your 0.005 and this is your 0.005. So, that makes total equals to 1. So, here we can have this value, and so that value multiplied by your s by square root n and added to that one will give you the upper limit, and subtracted from the mean will give you the lower limit. So, here that 99% confidence interval, the alpha by 2 is equals to 0.005. From the t distribution table, we get the values of t 0.005 comma 24. This value, when we are taking that cumulative probability equals to 0.995, and for f equals to, that is degrees of freedom, equals to 24. So, this p equals to 0.995 means if you refer to this one, that is from the minus infinity, the support of this t distribution, also you know that minus infinity to plus infinity. So, from this minus infinity to this point, the total probability that is covered is 0.99 plus 0.005, that is 0.995. So, that this value we are interested. What is this value? So, this is the value at which the cumulative probability is 0.995. So, this is the value that we are looking for, and this t distribution safe changes with respect to its degrees of freedom. So, for the degrees of freedom 24, this value is equals to 2.797. Now, if you recall that from our earlier example, that if it is a standard normal distribution, and then we have at this point 99% confidence interval, this value was 2.575. So, this is changed, and this change that you can see, this is basically for these degrees of freedom, that is 24. So, the lesser the sample size, lesser the degrees of freedom, and this difference from the standard normal to this t will be more. Now, if this is increased and it goes beyond 30, then we can see that this value and the corresponding value for the standard normal distribution are essentially same. That is why that 30 can be used as a judicial cutoff to declare that greater than 30 is the large sample and less than 30 is the smaller sample, for which we have to use that t distribution, what is done here. So, now okay, this will be s, as just now I discussed that this is a sample estimate. So, the s divided by square root n multiplied by t alpha by 2 n minus 1. So, this quantity now becomes at 4 by square root 25 multiplied by this value will give you that 2.24. Now, if we just take that, so this 99% confidence interval will be the difference between whatever the sample mean, which is 24. So, 24 minus 2.24 and 24 plus 2.24, that is 99% confidence interval is 21.76 and 26.24. Note that this interval is larger when compared to that where the standard deviation of the population was known. This is expected because the uncertainty is greater when the standard deviation is unknown. So, this was also we are mentioning in the last class when we are talking about this large sample and this small sample. So, you can see that if we have this if the sample size is small, that means that time your confidence to tell confidence to infer something will be lower. So, as this is lower, so you have to specify a wider interval to declare that okay, at this confidence level the whatever the actual value of this parameter can be captured. Now, we are comparing, if we compare now that same confidence level, one is then so the both are 99% confidence in interval that we are talking. Once we are using it for the large sample which is greater than 30 and we have used that normal standard normal distribution, there that confidence interval that if you see and if you compare it with that what we have seen now for the 25 samples size. So, this interval is more than what we got in the earlier, and this is because that we have having the less sample. So, our determination is less. So, we have to give a wider range to take care that with the same probability level this can be, that actual value can be captured. If the sample size even become lesser, so at the same probability at the same confidence level this limits this interval will be even wider. Okay, so now so far what we have seen is that basically that is called the two-sided confidence limit of the mean. So what is there that we are talking here is that, so this is the whenever we are talking about the confidence interval and then we are just comparing with respect to this central value, and whatever the confidence level that we have just put is basically what is symmetrical with respect to the central value. So, this area what we have declared as my confidence, and this is equated to what is my desired confidence level. Now, in many cases we may not interested of this both the side of this confidence interval. I may be interested, and particularly there are many civil engineering example that we will discuss now, is that we are interested only one side of this confidence. So, now if we want to know that what is the upper limit of the confidence level at this confidence when the lower side I am not interested. So, only the upper side. So, what is the one that is called the one-sided confidence. So, the same thing what we have to present here is that I need to know what is that point if I use that same confidence level, that is from this minus in infinity. So, from this minus infinity this is my confidence zone where it is 0.99. Now, this area in earlier case it was divided both sides. So, it is 0.005 here and 0.005 here. In this case when it is one side it is 0.1 when we are interested for the upper limit. And if we are interested for the lower limit, then the same thing we can plot, and we just interested to know. So, this side from this one to this plus infinity up to. So, this is your 0.999 and this area is your 0.01, sorry, this is 0.01. So, this is the lower limit and this is the upper limit, and this things is common in almost all the application field including civil engineering. So, in many real life problems in civil engineering only one of the confidence limit is of concern. Say for example, the upper limit of the mean wind velocity encountered at the top of this building. So, I may not interested what is the lower limit of this wind velocity. So, I want to know that what is the upper limit of the mean wind velocity, because I need the maximum load what the building can face. The upper limit of the mean traffic volume capacity of a highway. So, this mean traffic volume, if it is the lower side obviously is not of my interest. I want to know that what should be the maximum mean traffic volume that can be expected over a highway. The lower limit of the mean stress that can cause the failure in the steel specimen. So, in this case when it is the when the failure is my concern. So, I just want to know that what is the mean stress or what is this lower layer limit at which the specimen can fail. So, here we are interested only in the lower limit, upper limit of no interest to us. The lower limit of the mean dissolved oxygen DO in a stream for sustaining aquatic life. So, here the lower limit of this DO, that is whether that minimum requirement for this aquatic life is maintained in the stream or not, that I am interested. So, the upper limit of DO in such case is not of my interest. So, I need only one side of this confidence interval. So, these are some of these example where we are interested to know that what should be the their limits, either I am interested in the upper limit or in the lower limit. So, what is the change in this respective concept is that only thing is that from the whatever, if we are looking for this upper limit, then we have to start from this minus infinity to that point, that is my confidence level. So, that remaining part is 0.01. So, this 1 minus this confidence level. Similarly, for the lower limit, as contrast to the earlier case when when the confidence interval is symmetrical with respect to the central value. So, where this remaining probabilities is equally divided in the one side, in the upper side as well as from the lower side in the earlier cases. So, we will just see for such cases how we can get that confidence limits. Let that 1 minus alpha be the specified confidence level and the standard deviation of the population be sigma, the random variable x bar minus mu divided by sigma square root n follows the normal distribution. Hence, this 1 minus alpha lower confidence level of this mean mu is z minus z alpha sigma by square root n. So, you see that here also we know that standard deviation of the population is known, which is sigma. So, it will follow that standard normal distribution, and instead of using that z alpha by 2, we are using the alpha. And the upper limit, if we are interested, then that mean plus that z alpha sigma by square root n, as we have just now shown through the pictorial representation, where this z alpha is obtained from the standard normal tables. And if the variance is unknown, and this is basically for this smaller sample, then this 1 minus alpha be the specified confidence level, number of samples be n, and the sample standard deviation is this s, then this x bar minus mu divided by s by square root n, obviously this is from the sample estimate, s by square root n follows t distribution with degrees of freedom n minus 1. So, hence that 1 minus alpha lower confidence limit of the mean mu is x bar minus t alpha n minus 1 s by square root n. So, here you can see that it is, instead of in the earlier case we are using this alpha by 2. So, here it is t alpha, and with this n minus 1 is the degrees of freedom. And similarly, for the upper confidence limit is that x bar plus that this quantity t alpha n minus 1 s by square root n. So, this when this t alpha n minus 1 in both this expression, from here this t alpha n minus 1 and t alpha n minus 1 here that is used, this is basically is this value here, that we can see if it is a t distribution with degrees of freedom n minus 1. DOF degrees of freedom equals to n minus 1. So, this we are looking for, this value is your t alpha n minus 1, and this one is basically 1 minus alpha, this 0.99. So, this value we are interested. So, this one we are just taking this deducted from this mean, and this is added to the mean. Now, the confidence limit of this variance. So, I hope that this one that we have discussed for this upper limit and lower limit, just the small change that we are doing, that you can see, and the respective values should be picked up from the standard table. So, and then you can determine whether the upper limit or the lower limit, whatever is desired, that we can pick up. Next, we will move to the confidence interval of the variance. So, mean we have discussed. Now, the variance is also once we are getting from the sample. So, that also should follow some distribution, and we should know what distribution it follows, and we should know that what should be that confidence limit for the variance as well. For a normal population, so this is the background assumption that you can say that for a normal population, if the sample size n is small, then the exact confidence limit of the population variance sigma square can be determined as follows. So, the sample variance S square is, you know that this is the estimator that we have discussed last class, that is S square is equals to 1 by n minus 1 I equals to 1 to n xi minus x bar square. This x bar is the sample mean, and xi there are n samples are there, x1, x2, x3 up to xn. So, this is the way we get that unbiased estimate of this sample variance. So, this one as we get, and if we just take this n minus 1 just after algebraic manipulation, if we do that, then we can see that n minus 1 S square is equals to summation of these two quantity xi minus mu minus x bar minus mu whole square. So, after some step that we can express that this n minus 1 S square divided by sigma square can be expressed through this, that is I equals to 1 to n xi minus mu by sigma whole square minus x bar minus mu divided by sigma by square root n whole square. As xi is normal, so this x bar is also a normal distribution. So, you know that this we discussed in the last class, that is x bar is also one random variable which follows a normal distribution with mean and this standard deviation of the sigma by square root n. And even though these xi's are not normal, then also this the distribution of this x bar is approximately correct. But in case of the variance, that assumption is more crucial, that is the background that distribution of the population is normal. So, here you can see that this xi is normal, so x bar is also a normal. Now, if we just see this right hand side, so this is the left hand side of this expression, and this right hand side there are two components. What is the first term? If we just see, the first term is the sum of the square of n independent standard normal variates. So, xi is the normal distribution with mean mu and sigma is the standard deviation. So, this x minus mu by sigma is a standard normal distribution, and hence, so this is square, and we are summing up for this n such standard normal distribution. And we have seen in the earlier module of these functions of this random variable that summation of this normal distribution, if we sum up, if we square them and sum them for the n distribution, then the resulting distribution is a chi-square distribution with n degrees of freedom. And the second term again is also the square of the standard normal variate, and it follows a chi-square distribution with 1 degrees of freedom. Now, the summation of two chi-square distribution having this having two different degrees of freedom is also another chi-square distribution. So, what we can say from here is that this full quantity is one chi-square distribution with degrees of freedom equals to n minus 1. So, that is why this n minus 1 S square by sigma square, where S is the sample estimate of the variance and sigma square is the population variance, and their ratio multiplied by this n minus 1 is a chi-square distribution with degrees of freedom n minus 1. This is what is written here. So, this n minus 1 S square by sigma square is a chi-square distribution with n minus 1 degrees of freedom. So, once we know this distribution, then whatever the confidence limit and all, we should get it from the chi-square distribution. So, hence if we are interested to know the upper confidence limit of this population variance of sigma square is given by n minus 1 S square by sigma square should be greater than or equal to C alpha n minus 1 is equals to 1 minus alpha. Now, you see here this 1 minus alpha, this is the confidence interval that we are this is the confidence that we are looking for, and this one, this C alpha n minus 1 is the value of chi-square variate with degrees of freedom n minus 1 at cumulative probability alpha. So, these values we can get from this standard chi-square distribution tables, which is available most of the textbook, and thus the 1 minus alpha upper confidence limit of the population variance sigma square of a normal population is n minus 1 a square divided by c alpha n minus 1. So, once we get this value from this chi-square table, then we can, and this is from the sample estimate. So, we can get this value which is the upper confidence limit at 1 minus alpha confidence level. We will take one example with this, that is the daily dissolved oxygen DO concentration at a particular location on a stream has been recorded for 20 days. The sample variance is found to be a square equals to 4.5 milligram per liter. What is the 95% upper confidence limit of the population variance sigma square? So, the sample is known. From the sample we have estimated the variance, and that estimation is 4.5 milligram per liter, and the sample size is 20 days here. So, remember one thing here before I go to this solution, that when we discuss that this is the mean, when we discuss this confidence interval mean, and we have shown that this more than the sample size more than 30 can be treated to be the large sample, but for when we are talking about this variance, even the 30 is not sufficient to declare that this is a large sample. So, generally even the sample size is more than 30 also, we have to the degrees of freedom is always will be associated to this. And anyway, this is the chi-square distribution which we should get with respect to that degrees of freedom. So, here the sample size n equals to 20 as we have seen in this example problem, and the sample variance a square is the 4.5 milligram per liter. So, this n minus 1 a square by sigma square will have chi-square distribution with n minus 1 is equals to 19 degrees of freedom. So, we have to refer to the table of this chi-square where these degrees of freedom, generally the tables are provided with different degrees of freedom starting from 0 to at least some values up to 50 or so. So, we have to refer to those that particular distribution for this 19 these degrees of freedom equals to 19. Now, for which cumulative probability level that you are interested, that depends on your what confidence level that you are looking for. So, here the 95% confidence that we are looking. So, here the alpha value is equals to 0.05 and the n equals to 20. So, this degrees of freedom is 19. So, for this one, so C alpha n minus 1, that is C 0.0519. If we see it from table, you will see that it is the value is 10.1. So, if we use this value, then we can see that is n minus 1 a square divided by C alpha n minus 1 is equals to 19 multiplied by 4.5 divided by 10.1. So, 7.99 milligram per liter is the 95% confidence limit. This is upper confidence limit of this population variance is 7.99 mg. So, if we are now interested for this lower confidence level, for this 95% confidence level, then this value will change, and you have to find out that chi-square value for the same degrees of freedom at the cumulative probability equals to 0.95, and this will be obviously is higher than this 10.1. So, that lower limit will be lower than the lower limit will be the lower than this value what we have seen from this sample estimate, and this value will be higher than whatever we have seen it for the for this 0.05 cumulative probability level. Well, so next thing, the next one of this parameter that is also very useful in many distribution is the proportion. So, estimation of proportion is required in the situation where the probability is estimated as the proportion of the occurrence in a Bernoulli sequence. And we have seen that in the Bernoulli distribution, this one, the parameter that we use is the probability of success, and that is denoted as P. So, there we need to know what is the proportion. Here the examples are the proportion of the product in a manufacturing unit that meet the specific quality standard. So, what should be the proportion that I can say okay this much percentage of this product are pass in the quality test. Second is that the proportion of the traffic taking the left turn at a particular intersection. So, there are total number of vehicle we can count, and out of which how many vehicles are taking the left turn. So, in that way we can estimate what should be the proportion that is taking the left turn at a particular intersection, just to design the traffic at that particular junction. Now, let us consider that a sequence of n Bernoulli's trials x1, x2 up to xn, where the results of every trial can be either success or failure, that is 1 or 0 respectively. Here the probability p of occurrence of an event in such a Bernoulli trial is the parameter in the Bernoulli's distribution, in the binomial distribution. So, this p if we have to estimate. Now, so that estimate, that is xi can take the values as can take the either 1 or 0. So, that the whichever is a success that we are denoting as 1, and which one is failure we are denoting as 0. So, here again that I mentioned many times earlier, that success and failure are the arbitrarily selected. So, even that tossing a coin, head may be the success and tail may be the failure. So, that when you are calculating the proportion, it is basically nothing but that of that sequence, that 1 0, that these binary numbers, that arithmetic mean of those numbers, it will give you the proportion. That is what is estimated here, that is summation of all this xi and divided by n will give you that estimate of this proportion. Now, the expectation of this proportion, this estimate is that expectation of 1 by n and summation of these values, which we can write that expectation of all these each and every outcome, which are also again a random variable. And we know that for this Bernoulli's trial, each and every outcome is independent and having the same probability of the success. So, which we can just get that xi is equals to again that p, and which can be shown from this equation. So, this is p. So, this expectation of this estimate of this p cap is 1 by n multiplied by n p. So, there are n numbers of expectation, all the expectation are p. So, this quantity is n p. So, the expectation of this estimate is also is equals to p, and the variance if we calculate, then 1 by n square of this variance of this xi, and this expectation of x square is also that p, and so this is that 1 by n square, this multiplied by this n, this one is p and this one is p square. So, that p into 1 minus p divided by n, this is the variance of the estimate of this proportion. So, thus the variance of the estimator decreases with the increase in the sample size n, that you can see. So, this is the variance of the p cap, not the p bar, this is the proportion, and it is centered about the that population proportion p. Now, when n is large, that p cap follows a Gaussian distribution with mean is p and variance is that p minus 1 minus p cap by n. So, we have to that mean also it is from this sample. So, this we can, so where this p cap is the observed proportion from the sample, and the confidence interval of this p, once we know that this is having that normal distribution, then this p cap minus this mean divided by its standard deviation, which is nothing but p cap minus 1 minus p cap divided by n, that is the square root of the variance, and this should have the confidence limit of this minus z alpha by 2 up to z alpha by 2 with the confidence level 1 minus alpha. So, this we have discussed in this last lecture also, which is taken from the standard normal distribution, and this value we are looking for that particular quantile value where the at the confidence level at the cumulative probability level 1 minus alpha by 2. So, thus the confidence interval of the proportion is just after from this thing. If we just see the confidence interval of this p, then we will just multiply this quantity with this value and add it to this one. So, we will get that p cap minus z alpha by 2 square root of this standard deviation, the square root of this variance, that is standard deviation, and the upper limit is the p cap plus z alpha by 2 square root of p cap into 1 minus p cap by n. Now, if we take one example of this proportion and its confidence interval, during the inspection of quality of the soil compaction in a highway project, 45 out of 60 specimen that were inspected could pass the severe requirement. So, here the again this is a Bernoulli's process, where the one particular specimen may or may not pass the severe test, and out of 60 specimen 45 specimen has passed. So, the first question, what is the proportion p of the embankment that will be well compacted, that is pass the severe test. So, this is the point estimation, and that what we have seen, the point estimation is just the ratio of whatever the number of success divided by total number of specimens. So, that we can estimate. And the second thing is what is the 95% confidence interval of that p. So, that we will see, we have to use the standard normal distribution. Now, you can see that the point estimate of proportion p of the embankment that will be well compacted, that is p cap, as I told that it should be the 45 divided by 60 is equals to 0.75. This is straightforward. Now, the 95% confidence interval of this p is that this estimate minus this z alpha by 2 into this their standard deviation, and p cap plus z alpha by 2 multiplied by its standard deviation. So, this alpha by 2 in case of 95% confidence level, that we have seen in this last lecture also, which is 1.96. So, 0.75 minus 1.96 square root of this, and 0.75 plus 1.96 square root of this magnitude, which is the variance of this estimate. So, if we do this one, then we will get that this quantity becomes 0.64 and other one become 0.86. So, the confidence interval for the estimate of this proportion p cap is 0.64 and 0.68, and that you can see that it is symmetrical with respect to that estimate 0.75. So, more if we increase this confidence interval to say for example from 95% to 99%, then it may go, it will go wider. This one will be even become lower and this one even become higher. So, this at 95% confidence interval, this confidence limits are 0.64 and 0.86. So far we have discussed about the point estimation, and in this lecture we have discussed about this interval estimation of this parameter. Now basically what happens, these estimation when we are doing with the respect to one data set that is available to us. Now suppose that there are two data sets are available to us, and some type of we may sometimes interested to know that whether the mean of that population can be like this or it cannot. So or I can even say that whether whether I can say that two populations are coming, two samples are coming from the same population or not. That means they are the parameters that is associated with the population and what we are getting from those samples, those are same or not. So to answer this type of question, what we need that is known as this hypothesis testing. So that is what is our next interest that we will discuss now. So this is your in this hypothesis testing in real life decision making, it is often necessary to decide whether a statement concerning a parameter of a probability distribution is true or false. This hypothesis test is used to check the validity of a possibility or guess, means like that kind of English word that we are using, which is basically is known as this hypothesis of one possibility. Yes, this may happen like that. So about the population, so that the necessary decision can be taken depending on the test result. Suppose that for example, if I take on this point one civil engineering real life scenario is that suppose that I am estimating the strength of a concrete, and so what we are supposed to get is that I need, say for example, for a specific requirement I need the strength should be greater than some threshold value that we know. Now how to test that one? So we have to take some sample and we will get, say that some sample mean. So now we have, now the sample mean may or may not cross that that particular threshold value, or it may be the difference from this whatever our expectation and what we are getting from this sample obviously will not match. As soon as we are changing the sample also, that will that will change. So depending on that, now we have to test whether that that difference that we are getting, is it by chance or there is some problem in the construction itself. So depending on that, after this test result of this hypothesis testing, that we have to decide that what is that, whether it is by chance that the difference that we got or there is some problem in this problem. So what we are targeting, what we are trying to test, that is whether the strength can be assumed to exceed that threshold value. So that possibility, that guess is known as what is the hypothesis here. So that hypothesis we have to test, and depending on that test result, we have to take some necessary decision, whatever we can take in that. So these decisions are basically based on the statistics and known as this the statistical inference that we can draw from the whatever the sample data that we are having. Say when a probabilistic model is developed to describe some process, say for example, we can take we will take in this coming lectures, after few lectures we will take that regression. So which is the which is one of these very important model. So there, if we just express those expressions, then that model whether that is exactly matching with this data or not. So that probabilistic model which we have developed, it may be found that the observed data set matches partly with the model. In such cases, the deviations from the observations from the model may be due to two cases. One is that actual inadequacy of the model or some chance variation. So these two are important. The actual inadequacy of the model, if we can declare this one, then we have to seriously think about that we have to change the model, and we have to that model should be changed so that we can better explain the process. On the other hand, even though the model is correct, it will never match with the observed value, with the observed data set. So that variation is called the chance variation. So in such cases, that is when it is varying, whether it is varying by chance or if there is some real inadequacy is there in the model, for that case this hypothesis testing is used as a statistical test to determine whether the device model is adequate or not. There are two types of errors are there in the hypothesis testing. These are known as the type 1 error and type 2 error. So the true hypothesis gets rejected. So the hypothesis that we are first assuming, so if say that is actually correct, and through this test, through this hypothesis testing, if we reject it, that means that we are facing one type of error, and that is known as this type 1 error, and the probability of this type 1 error is denoted by alpha. Similarly, when the hypothesis is false, but we fail to reject that hypothesis, that time also we are doing another error, and that is known as this type 2 error, and probability of type 2 error is denoted by beta. So if I just see through this table that the true situation, the hypothesis can be true or the hypothesis can be false, and the decision that is taken after the hypothesis testing, that we fail to reject the hypothesis. So, if we fail to reject the hypothesis in case when the hypothesis is true, then obviously there is no error. So, we have taken the right thing has occurred. Now, if we fail to reject the hypothesis and the hypothesis is false, then that is the type 2 error as we have explained here. On the other hand, if we reject the hypothesis and the hypothesis is true, then also this is one type of error which is known as the type 1 error. And if we reject the hypothesis and hypothesis is false, then also there is no error is occurred. And this type 1 error is, the probability of this type 1 error is alpha, is denoted by alpha, and probability of type 2 error is denoted by beta. Now, you can see that this type 1 error, when it is the hypothesis is true and we reject the hypothesis, basically from the manufacturer point of view, this type of error is very critical, and we generally try to we generally allow very low value for this type 1 error, and after giving this one, we try to minimize as much as we can for this type 2 error. So, the steps of this hypothesis testing is there are the following systematic steps, the steps we can follow in this hypothesis testing: the formulation of a null hypothesis and an appropriate alternative hypothesis which is accepted if the null hypothesis has to be rejected. So, the definition of this null hypothesis and what is null hypothesis and what is alternative hypothesis we will see in a minute. Only one point that we should note here, that whatever we are putting in this null hypothesis, we can say that we are either we should reject that null hypothesis, or we should say that based on the data available we fail to reject the null hypothesis. Generally, we cannot, it will be wrong to state that this null hypothesis is accepted. So, as we cannot declare that this null hypothesis is accepted, maximum what we can say that we fail to reject this null hypothesis. On the other hand, what we can say that null hypothesis is rejected. When we say that null hypothesis is rejected, that time we can accept this alternative hypothesis. So, in this hypothesis test, whatever the hypothesis that we want to test is generally put in this alternative hypothesis, so that at the end of this test, if the null hypothesis is rejected, we can say that the alternative, what basically we are trying to test, we can accept that hypothesis. So, whatever our goal, whatever we are trying to test is generally put in the alternative hypothesis. Specifying the level of significance, this is the second step. Once we have clearly defined what is my null hypothesis and what is my alternative hypothesis, I have to define one level of significance, that is the probability alpha of the type 1 error. As we just now told that our goal is to that for this type 1 error we should minimize as much as we can. So, generally this alpha we can assign the value of 5% or 1% like that. So, alpha equals to 0.05, alpha equals to 0.1, these are the typical values of this alpha that we can fix. Of course, in some cases, some alternatives, the probability of beta, that is probability beta of type 2 error may also be specified, but in general case what we do is that level of significance is generally predetermined before we go for this hypothesis testing. Then construction of criteria based on the sampling distribution of a suitable statistics for testing the null hypothesis. So, that suitable statistics that we have to develop, and we should know what is the probabilistic nature of the statistics. In the earlier discussion of this parameter estimation, there also we have developed some statistics, and we have seen that what is the sampling distribution of different statistics. So, similarly here also the suitable statistics for this test we have to construct, and depending on their probabilistic distribution, we have to find out what is the critical value for that. So that so this suitable statistics has to be constructed. Then calculation of this value of the statistics from the data. So whatever the statistics that we have decided for the hypothesis test in hand, for that one, whatever the observed value that we are having, based on which we are testing this hypothesis, that statistics value should be obtained. And after that, and the final step is for this decision making, that is reject the null hypothesis, or we can say that fail to reject the null hypothesis. So, as we are telling that using the two words, that's null hypothesis and the alternative hypothesis. The null hypothesis is any hypothesis that is tested to see if it can be rejected. It is denoted by H naught. The alternative hypothesis is that which is accepted if the null hypothesis has to be rejected. It is denoted by HA. Alternative hypothesis may be one sided or two sided. We will see that one, what is one sided and what is two sided here. So, what we are just discussing, that in case we can reject the null hypothesis, then we accept this alternative hypothesis. We never say that the null hypothesis is accepted. So, that is why whatever our goal, we generally put it in the alternative hypothesis. Now, the example of this one sided and two sided that we will see, let us consider that a mix of concrete is acceptable for a certain construction only if the mean strength is greater than 25 kilonewton per meter square. So, that so if this is the threshold value, and I say that only if it can be greater than this one, then only it is accepted. Whether based on this sample data we should decide or we should accept that yes, the strength is greater than 25 kilonewton per meter square or not, that we will see. So, that is why in the alternative hypothesis we put that mu is greater than 25. So, the mu is greater than 25 is in this alternative hypothesis. So, in the null hypothesis, the remaining thing, that is less than equals to 25, is put there in this null hypothesis. Remember that here it is acceptable only if the mean strength is greater than 25 kilonewton per meter square is written. If it is written that it is greater than equal to 25 kilonewton per meter square, then in this one sided alternative hypothesis, this equality sign we put here, that is mu greater than equal to 25, and here in this null hypothesis we write that mu less than 25. So, depending on this statement, what we are trying to test, that will be exactly written in this alternative hypothesis. Similarly, the example of two sided alternative is, let us consider that in a cement plant the average amount of cement in one bag should be 50 kg. Now, if we want to check whether the average amount is not much greater than 25 kg, so if it is more than 25 kg, this will be the loss for the manufacturer, or it should not be much less than 50 kg as well, because this will dissatisfy the customers. Then what we are trying to test is that whether we can accept that this is that check that whether per bag the amount is 50 kg or not. So, in this null hypothesis it is written that mu is equals to 50, and two sided alternative hypothesis that we write is mu is not equal to 50. So, in this case, if we fail to reject that null hypothesis, then the job is done, in the sense that manufacturer is happy, yes, the mu equals to 50 kg, that is 50 kg per bag, whatever the sample that we have taken cannot be rejected. Level of significance, a hypothesis testing is always associated with a level of significance. It is equal to the probability alpha of this type 1 error. So, as we have discussed earlier, this value of this alpha is generally fixed at 0.05 or 0.01, but may vary depending on the consequence of committing the type 1 error. If the chosen value of alpha is too small, then the probability of type 2 error is generally increases. p-value. The p-value for a given test statistics and the null hypothesis is the probability of obtaining a test statistics value that is equally extreme or more extreme than the observed value. For a right side alternative hypothesis h1 equals to say mu is greater than some threshold value mu naught, only the values greater than the observed value of the test statistics are considered for more extreme, and for a left sided alternative hypothesis when its mu is less than some threshold value, only the values lesser than the observed values for the test statistics are considered more extreme. For a two sided alternative hypothesis, the values on both the tails are considered more extreme. So, basically if you see that p value, suppose that this is the distribution of the statistics that we are considering. Now, in this if you just see that the test statistics comes this value, then this is your basically the test of significance at this level. So, which we generally fix at 0.005 or 0.01 as the case may be. Now, suppose that the test statistics is falling in this zone, then the p value whatever is remaining here for the one sided test, the p value is this green highlighted area. So, this area is known as this p value. This is for this one sided, obviously the upper side. Similarly, it can happen for this lower side also, or if it is a two sided test, then the symmetrical value we have to take here, and this area also should be included for that, for the calculation of this p value. So, once we set this significance level, then we get what is the zone. So, if the test statistics fall in this zone, then we should reject the null hypothesis, and if it falls, if it does not fall in this critical region, the blue highlighted is the critical region for this any significance level, then we cannot reject this null hypothesis. So, well, we will continue with this one, with this discussion of this hypothesis testing in the next lecture also, and we will take up some problems also, and various hypotheses concerning two means, one variance or two variance, this type of problems we will take in the next lecture. Thank you.